Biological snakes are pervasive across the planet. Their diverse locomotion modes and physiology make them supremely adapted for the wide variety of terrains, environments, and climates that they inhabit. While wheeled and walking machines have undergone many years of development, they are still limited in the types of terrain they can traverse. A snake-like device that could slide, glide, and slither could open up many applications in exploration, hazardous environments, inspection, and medical intervention. Some problems with the design of snake-like robots arise due to their many degrees of freedom. This makes the kinematics, dynamics, and control of snake robots somewhat complex. In this project, we explore the kinematics and dynamics that make snake-like robotic movement possible.
There are various ways that a snake can move. The easiest one to understand is the obstacle-aided locomotion, because snakes basically push against the obstacles and move forward by the sum of the reaction forces. The most common one, and the one that most people put emphasis on, is the lateral undulation, when snakes moves almost like a sine wave. In order to make movements like this, the normal friction coefficient has to be greater than the tangential one. Biologically, it is done by the arrangement of the scales on the belly of snakes. When trying to mimic the same movement, people tend to use wheeled snakes to accomplish this constraint. We can use Euler-Lagrange equation to calculate the whole impact of friction forces on the snake body and the resulting movement. By summing up all the forces on every link, most of the action-reaction friction forces cancel out and the head movement can be easily derived.
We built a block diagram using Simulink and SimMechanics. SimMechanics includes the links, joints, actuators, and sensors to build a snake robot. The friction subsystem uses measured velocity to calculate friction forces. We actuated the joints with the sine function described in the math section. This is what a simulation of the snake robot looks like. This is a graph of the normal and tangential forces. As you can see, the normal friction force is much higher than tangential, which is consistent with the snake's motion.
We also work with a commercial available animation software package called VRAP, using a pre-built snake robot to simulate the gait of snake robots. We use the wheelless snake robot to simulate the side winding gait. Since the robot model does not have scales and skin to provide more forward frictions, it's difficult to move forward in simulation. The AC-arm snake robot, which has passive wheels, can move forward and even swim in the water.